Welcome friends to this second week of lectures for environmental soil chemistry, and our topic for this week 2 of lectures is inorganic soil components. So, basically we will be discussing about different inorganic components which are present in soil, and so these are the concepts which we are going to talk about in this week. First of all, we will be talking about Pauling's rules, which are very important for understanding the structure of different minerals. Then we will be talking about primary and secondary clay minerals and or soil minerals. Then specific surface of soil minerals we will talk about, and then we will talk about the surface charge of soil minerals, and then finally we will be talking about identification of minerals by X-ray diffraction analysis. So, these are the some of the topics which we will be covering in this week, and so let us start from the composition of the soil. Those who have already know about our introductory soil science and technology course in NPTEL, we have already discussed about the composition of the soil, but let us see again what is the basic composition of the soil. You know that soil is composed of both solid components as well as pore spaces, and the solid components are basically occupied by different inorganic and organic matter, and pore spaces are occupied by water and air interchangeably. The inorganic components of soil basically composed of different primary and secondary minerals, and they are basically concentrated in three soil separates, for example sand, silt and clay. So, these are the major three soil separates where these inorganic components are concentrated, and so if you see the volume wise soil composition, you will see that the 50% of the soil volume is occupied by the solid component, whereas the 50% of the rest 50% pore space is occupied by water and air interchangeably, and in case of ideal condition there will be 25% of air soil air and 25% of soil water, and among this 50% inorganic compound will be only 45 inorganic compound will be 45%, whereas organic matter which are basically composed of microorganisms, macroorganisms and humus will account for only 5%. So, this is the volumetric composition of soil. Now, in this week we will be basically discussing or focusing on this 45% inorganic mineral matter which are very important for soil. So, the first question comes, what is a mineral? Remember, a mineral is basically a natural inorganic component with definite physical, chemical and crystalline properties. So, to be qualified as a mineral, a compound has to be a natural inorganic in nature, as well as they should have definite physical, chemical and crystalline properties. So, let us move ahead and see what is the major classification of the minerals. Well, we can classify the minerals into primary minerals and secondary minerals. Okay. So, what is the difference between primary mineral and secondary minerals? So, the minerals which have not been altered chemically since their deposition and crystallization from the molten lava are known as the primary minerals. You know that all the minerals are developed from weathering of the rocks. So, these minerals or primary minerals are basically are composing the rocks. So, they when they do not change their chemical structure, and retain their original chemical properties, then we are calling them primary minerals. For example, the most important primary mineral which are present in the earth crust are quartz, feldspars and pyroxenes, olivines, micas. So, these are very important primary mineral. And remember that quartz is the most wide dominant primary mineral, followed by feldspars, and these primary minerals mainly found in sand and silt fraction. So, these primary minerals basically compose the sand and silt fraction, which basically form the skeleton of the soil, and the sand and silt fractions are chemically non-reactive or inactive. Now, when this primary mineral, due to different types of chemical processes and other processes, changes their chemical structure, then they are called secondary minerals. Now, remember the important soil separate clay is basically composed of these secondary minerals. So, these minerals are basically obtained from weathering of the primary minerals, and most important feature is their change of their chemical structure or chemical nature. Example is kaolinite, montmorillonite, gibbsite, goethite, and they are mainly found in clay fraction, as I have already told. So, again primary minerals are concentrated in the sand and silt fraction, and sand and silt fraction basically produces the skeleton of the soil, whereas secondary minerals also known as clay minerals, because they composed the clay, and these secondary minerals basically form from the weathering of the primary minerals, and their chemical structure has been changed, and these clay fractions or clay mineral basically produces or basically compose the flesh of the soil. So, this is the difference. So, these two tables basically shows different primary and secondary minerals which are present in the soil. So, if you see the and also their corresponding chemical formula. So, as you can see from here, the most common primary minerals are quartz, which has a which is a formula of SiO2, followed by the feldspars, and muscovite is another important primary mineral. Then biotites, feldspar are of different types like orthoclase feldspar, microcline feldspar, albite, then amphiboles, tremolite, pyroxenes. Among the pyroxene, these are basically uh, and there are different types of pyroxenes, as you can see: enstatite, diopside, rhodonite, olivine, which is a ferromagnesian mineral, epidote, turmalin, zircon, rutile. All these are different types of primary minerals, and these primary minerals you can see in the original composition of the rocks, because they are mainly the rocks are mainly composed of these primary minerals, and unless the chemical nature of these primary minerals change, they are not termed as secondary minerals. So, once due to different types of chemical weathering or chemical transformation, the nature and the chemical structure of these components change, then they become the secondary minerals. What are the important secondary minerals? Clay minerals. Clay minerals, some examples are kaolinite, montmorillonite, vermiculite, chlorite. We will discuss them. Also, allophane. Allophane is a non-crystalline clay mineral. Also, imogolite, goethite, hematite, then magnemite, ferrihydrite, bohemite, gibbsite, pyrolusite, bernicite, and then dolomite, calcite, gypsum, jarosite. So, all these are different types of secondary minerals, and these secondary minerals are basically developed from the primary minerals due to decomposition and weathering process, especially chemical weathering process. So, all these are having specific chemical formula, and so the secondary minerals are again mainly present in clay fraction, whereas primary minerals are present in sand and silt fraction. So, while discussing about the structure of a mineral, the most important thing we have to consider is some basically rules which governs the structure of that mineral. Now, most of the mineral structure in soils are ionically bonded and their structure can be predicted based on Pauling's rule given by Pauling in 1929. This picture shows the famous scientist Linus Pauling, who has developed these rules which basically shows the structure of of a mineral and how they are built of and what are the different conditions they need to satisfy to form a structure. So, we know that there are two types of bonding present in mineral structure. One is called ionic, another is covalent. Remember that majority of the mineral structure in soil has a ionic bonding. And when the bonding in a mineral is principally ionic, its structure is fairly simple because the ions then may be regarded as rigid spheres. So, in that case, in case of ionic bonding, we assume that these these ions can be considered as rigid spheres. We'll see in a while. We'll see very shortly. And the geometry of these rigid spheres is governed by Pauling's rules. So, we will be discussing these rules. So, there are a couple of rules, let us talk about them one by one. So, Pauling's rule, before learning about the Pauling's rule, let us discuss about two important things. One is radius ratio, another is coordination number. So, if you can see here, radius ratio is basically a ratio of a radius of the cations by radius of anion. And coordination number is basically the number of nearest anions surrounding the particular cation. So, these two are very important factors while discussing the Pauling's rule number 1. So, what rule 1 says? So, the rule 1 states that a coordinated polyhedron of anion is formed about each cation and the cation anion distance being determined by the radius sum, which is basically sum of cation and anion radii, and the coordination number of the cation is governed by the radius ratio. So, again a coordinated polyhedron of anion is formed about each cation when the cation anion distance being determined by the radius sum and the coordination number, which is the number of nearest anions surrounding the cation, will be governed by the radius ratio. So, what does it actually mean? So, let us see in details. So, according to the radius, sum of the radius of cations and anions, you can see here the cation anion distance is basically governed by this cation by the summation of their radius, as you can see here. Because this is ionic in nature, this bonding is ionic in nature, we are assuming that these cations and anions are having rigid sphere like structure. Now, remember that since ion tends to surround themselves with many oppositely charged ion as possible, predicting coordination number requires using only the relative size of ions, which is expressed as a radius ratio. So, this radius of these cations and anions are very important while determining the coordination number. How? We will see now. So, again let us come back to coordination number. Coordination number basically depends on the relative size of the ions, because the radius ratio we have already talked about it. So, if all atoms in a crystal are the same size, then there are two ways to pack the atoms to form a crystal structure. So, let us assume that there are 6 atoms and all these atoms are having the similar size, then there are two ways to pack the atoms to form a crystal structure. Now, in this case, the maximum number of atoms that can be coordinated around an individual is 12 in this way, if we stack 2 layers. So, in that case, we will call it a 12-fold coordination. Now, there are two ways that atoms can be packed in a 12-fold coordination. There are two ways that the atoms can be packed in a 12-fold coordination, and we will see that. So, the first, before discussing those two ways, let us discuss another important point, that the single layer of atoms of equal size, which we have seen in the last slide, if this is a single layer of atom of equal size, let us assume this is an A, these atoms are denoted by A, then two kinds of voids are present in between these atoms. As you can see, this is one kind of void and this is another kind of void, and we are renaming these, naming these as B voids and C voids. So, all these voids are triangular in shape, and you can see these B voids are pointing up, and the triangles which are pointing down are known as the C voids. So, these two types of voids are created when there is a 12-fold coordination with single layer of atoms of equal size. So, if we if we have this single layer of atoms of equal size, then this 12-fold coordination can be expressed in two ways. We call them closest packing. There are two types of packing. One is called HCP, another is called CCP. HCP is the short form of hexagonal closest packing, whereas the CCP is the short form of cubist closest packing. So, let us first discuss the hexagonal closest packing. So, if you see here, if we add, so we first had a single layer of similar size ions, which is denoted by A. So, if we add a next layer, this is the next layer of atoms, so that they occupy the space above the B voids. If you remember the B voids, so you can see this second layer is occupied the space above the V voids, and then again we add the next layer above these A atoms. So, if you can see here, this will give you more clear picture. So, we are having a layer of A atoms and then a layer of B atoms and then again a layer of A atoms and B atoms. So, alternatively they are repeating each other, and these B atoms layer are basically placed above the B voids. It is not directly placed above the A atoms. So, this type of stacking basically result in a sequence of AB, 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 etc. Sometimes we call it ABC also, I am sorry, ABA. So, this type of stacking is known as AB, AB, or sometimes we call it ABA type of stacking also. So, this type of closest packing is referred to as the hexagonal closest packing or HCP. It results in a hexagonal lattice with the C axis oriented perpendicular to the ABAB layers. So, this is one of the way of producing this 12-fold coordination, that is hexagonal closest packing. Now, let us consider the second scenario. So, first we had these A layers and then we add these B layers on the top of B voids. So, if after adding the layer of B atoms, we place the next layer so that the atoms are occupied the position over the C void. So, there are two types of void, B void and C void. So, the second layer is placed over the B voids and the third layer is placed over the C voids, and continues the process upwards, we get a stacking sequence that runs ABC, ABC, ABC. So, in case of HCP, we got a stacking sequence of AB, AB or ABA, whereas in case of CCP or cubist closest packing, we are getting a stacking pattern of ABC, ABC. Just like here you can see, this is a layer of atom, then B layer and then C layer, and then from the top we will see the stack layer just like this. So, this is called the cubic closest packing or CCP. So, this is another way of representing the 12-fold coordination. So, it results in a cubic or isometric lattice with the axis perpendicular to the layers. So, now we have seen the 12-fold coordination. What is a 12-fold coordination? Then hexagonal closest packing and cubic closest packing. So, let us move ahead and see them side by side. Again, this is a ABA hexagonal close packed, you can see it is a layer which is basically at the below the B layers, and then A layer. So, it is a repetitive A layer, B layer and A layer. It is a hexagonal close pack. In case of CCP, it is basically A, B and C. So, this is the difference in their structure or stacking arrangement. So, what is the implication of radius ratio in this structural arrangement? Remember that the relative sizes are indicated by the radius ratio of the coordinating atoms or ions. Now, in the crystal structure, we usually look at the cation surrounding by the anions. So, the radius ratio is basically defined by Rx by Rz, where the Rx is the radius of the cation and Rz is the radius of the surrounding anion. So, again this radius ratio is basically Rx by Rz, where Rx is the radius of the cation, whereas Rz is the radius of the surrounding anion. So, basically radius ratio is again it is the ratio of ratio of the radius of the cations to the radius of the surrounding anions. Now, since the anions are usually larger, here you can see the result is decreasing the values of Rx over Rz as the size of the cation decreases. So, when the size of the cation decreases, obviously this radius ratio further goes down. So, what is the problem in that? So, once this radius ratio goes down, due to the decrease of the size of the cation, so there is some changes. So, if we decrease the size of the cation in such an arrangement, still allowing the surrounding anions to touch each other and touch the cation with decreasing size of the cation, the coordination will first result in 8 anions surrounding the cation. So, earlier we started with 12-fold coordination. Now, we are moving towards 8-fold coordination, because due to the decrease of this cationic size, we are now surrounding the cation by only 8 anions, as you can see here 1, 2, 3, 4, 5, 6, 7, 8. So, this is called a 8-fold coordination or cubic coordination. Because it is called cubic coordination because the shape of the object is constructed by drawing the lines through the center of the larger ion is a cube. So, now we have seen how we can change from a 12-fold coordination to 8-fold coordination to get a cubic arrangement. Now, while we are discussing this, another important aspect we have to discuss is called the limiting radius ratio. Now, if the size of the coordinated cation becomes smaller, it will become too small to touch the surrounding anions. Because when it is becoming too small, it may not be able to touch the surrounding cations which are larger in size. So, that there is a term called limiting radius ratio that will occur when Rx by Rz becomes too small. So, the radius ratio for the limiting condition often called the no rattle limit, because if the radius ratio becomes too small or smaller than that cutoff value, then the cation will rattle, or basically they will rattle in its sides. So, that is why there is a specific terminology called no rattle limit. So, as you can see here, there are 4 anions surrounding a cation, and so the condition or this no rattle limit for these 8 coordination or cubic arrangement can be achieved by using the Pythagorean theorem. So, this limiting radius ratio can be calculated by using this Pythagorean theorem, whereas this 2 Rx plus 2 Rz is the total distance, and then it is basically the square terms of this is a combination of these 2 Rz square this and this distance, that is 2 root 2 Rz square, and from there we got an Rx by Rz value of 0.732. So, this ratio, that is 0.732 is the cutoff, and anything if the radius ratio goes below 0.732, the cations will be too small or will rattle in its size in its site, and the structure will collapse, and then it has to change to a 6-fold coordination. So, this is the implication of limiting radius ratio. So, if the radius ratio goes beyond or goes below a certain limiting no rattle limit, then the coordination will change from one form to another form. So, again this when the radius ratio goes below this 0.732, then the 8-fold coordination will change to 6-fold coordination. So, we have seen how this 12-fold coordination will change to 8-fold coordination to 6-fold coordination. So, guys, let us wrap up here today, and in the next lecture we will start from here, and then we will see how other coordination compounds can be achieved by changing this limiting radius ratio, and from there we will discuss the structure of different clay minerals. Thank you very much.